This video is on the current second balance for capacitors in DC steady state. I hope that you have already watched the video on volt second balance for inductors, and this video on current second balance is very similar to that of volt second balance in inductors. And that is because you know that the inductors and capacitors are dual elements. So if you have fully understood the volt second balance for inductor in steady state, then you have already understood the current second balance as applied to the capacitor. Okay. So a lot of the discussions, the derivations, examples, they would be they're the dual of what we saw in the volt second balance. In particular, in volt second balance, we saw that the average inductor voltage VL average in steady state is 0, and its dual is what you're going to see here is the current through the capacitor, and its cycle by cycle average value IC bar is 0 in DC steady state. So here is the actual statement of the current second balance principle. It states that the average CCA average of the current through a capacitor in DC steady state, actually I should emphasize that again, in DC steady state is 0, or as a mathematical expression, IC bar, the bar denotes the cycle by cycle average, IC bar is 0 in DC steady state. So again, we have to remember three key elements in this statement. First thing is we are talking about the average, so this is covering the entire switching period, and only the average, not the instantaneous. The second one is it is the current through the capacitor. The voltage does not have to be 0. The average voltage is not 0. And this is valid only in DC steady state, not valid in transients or in AC steady state. Okay. The derivation of the current second balance is straightforward as in the case of the volt second balance in inductor. So as before, we start with the basic VI relationship for a capacitor, which is IC is C dV over dt instantaneously, or take its integral form. So VC at any time t is VC at arbitrary starting point t0 plus 1 over C times the integral of the capacitor current integrated from t0 to t. And as before, we substitute t equals t0 plus ts, so we are considering one complete switching period. So if we did that in equation 1, we get this equation 2, where we see TO plus TS is the starting value plus 1 over C times the integral of the current. Then we invoke the DC steady state principle that all waveforms repeat exactly from one cycle to the next cycle. Therefore, the capacitor voltage at T0 plus Ts at that instant is exactly same as the capacitor voltage at T0. So that is the definition of DC steady state. So substitute this 3 into 2. So we have this term is equal to this term. They cancel each other. So this integral term is 1 over C times integral term is equal to 0. Okay. So that is shown here. And again, if you multiply this by Ts and divide by Ts, then we get this term, including that 1 over Ts term, is nothing but the IC bar, the cycle by cycle average value of IC. So therefore, Ts over C times the IC bar is 0, or the IC bar, cycle by cycle average value of capacitor current, is 0, and this is only in DC steady state, and that is because right here we invoked the definition of DC steady state in order to come up with this expression. Another way to derive this is to work directly from the voltage current relationship in a cycle by cycle average sense. So IC bar is C times d over dt of VC bar, and in steady state, by definition, all quantities, all average quantities have to be constant. Therefore, the rate of change of VC bar is 0, which implies IC bar is 0. Okay. Again, it is very important to understand that when we say the average capacitor current is 0, it does not imply that instantaneously the capacitor current is 0. And as we saw in the volt second balance case, that's the difference between a switching converter and a non-switching circuit. So in a non-switching RL circuit, for example, the capacitor current instantaneously is 0. That's why we can actually replace a capacitor by an open circuit in DC steady state for non-switching circuits, whereas in switching converters it is only the average, and that was the average taken over one complete switching period, that is 0. So instantaneously, as seen in this example here, the instantaneous current can be either a very large positive value or a very large negative value, such that the area under the positive portion, which is this area A, is exactly equal to the area under the negative portion, the area B in this figure. So A and B, the two areas are exactly equal, so they cancel each other to result in the average IC being 0, IC bar to be 0. And the way we write the current second balance equation is shown here. So given this type of waveform, so in this example at least, it is given that the current is a constant value during, for example, the on interval at a magnitude of I1, and it's also another constant during the off interval of value equal to I2, and if I1 is positive, I2 has to be negative. Okay? So it may not be the case in all the waveforms, but if given this waveform, the current second balance equation would be I1, the on time magnitude, times D, which is dTs over the entire Ts, or the ratio of this duration over to the complete switching period, plus the magnitude during the off interval I2 times the ratio of the off duration to the total period, which is 1 minus T. And the sum of these two is nothing but the average value of IC bar, and that by the current second balance in DC steady state is equal to 0. Now, if as I mentioned, you may have cases where the current is not exactly a constant during the on interval or the off interval. For example, you may have a current value something like this. Okay? And this is also very often seen in practical power converters. So this is very often just the a part of the inductor current which has this kind of a wave shape during a part of the switching period. So still the current second balance holds good. All we have to say is this form of the current second balance expression, that is area under the positive part is equal to the area under the negative part, A equals B. So if the current second balance is satisfied, meaning IC bar is 0, then so that's the example shown here. So I have a switching waveform as the current applied to a capacitor. So during the on interval, again this is very similar example as the volt second balance case, Ts of 10 microsecond, and D is 1 over 3, and this is the dTs duration. This is the 1 minus D times Ts duration. Okay. So here the current second balance equation was 20 times 1 over 3, the D, minus 10 times 1 minus D, 2 over 3, that is equal to 0. And as a consequence, the voltage, the capacitor voltage, its average value remains constant. Okay, so I've given some initial condition, initial value for the capacitor voltage, so that's 25 volts. Starts at 25 because of the positive current, the voltage increases, and at this instant, at the end of the on interval, I apply a negative current, so the capacitor voltage falls with a slope M2 equals minus, the slope is always Vc over C, so in the off interval the slope is minus 10 amperes over the capacitance C. So the main point is, at the end of one switching period, the voltage comes exactly back to the 25 volts at which it started that particular period. And as you can see from cycle after cycle, the capacitor voltage average does not change. It always starts 25, comes back to 25. Now, if I apply a case where IC bar is not equal to 0, the average value actually is positive as shown in this figure. Actually, there is no negative current at all, therefore the average is clearly a positive. So if you look at the corresponding voltage, capacitor voltage, you can see that its average value is monotonically rising. When you apply this positive current pulse, the voltage begins to rise, and when the current is 0, the voltage remains constant at this value. Then again a positive pulse increases, and so on. So the voltage continuously increases, and that is non-steady state. In fact, this is what happens during the, for example, the startup of a power converter. We start with 0 voltage across the capacitors, and the way the capacitor actually builds voltage is going through this transient where the IC average is not 0, it is a positive value, so that the capacitor can eventually charge to its steady state value, and after that IC bar would be 0. That's what happens in most power converters. In the volt-second balance principle for an inductor, we saw that when we have a diode directly across the inductor, an ideal inductor, then that circuit will not result in steady state. The reason was, in that case, the VL average will be a positive value, and the current, inductor current would continuously rise. The dual of that in the capacitor case is, so if we have a diode in series with a capacitor, then this circuit will not result in a DC steady state, and that is because this diode would only allow a positive current into the capacitor, charging it, but it will not allow a negative discharging current. Therefore, the IC average will not be 0, it will be positive if I define the current to be positive entering the capacitor. Okay, so let's do an example problem to complete this video. So obviously this is going to be on the application of a current second balance in a capacitor in DC steady state. So we have a valid network, and just the capacitor is brought out, and we are given that the circuit is in DC steady state, and we are also given the waveform of this capacitor current IC. And the question is to calculate this value of D. The D is the duty ratio, and it is defined here, this interval where the current is positive, that is the D times TS interval, and the duration where the current is negative is 1 minus D times TS duration. So we notice that the capacitor current is not a constant value during this positive interval, during this on interval, and it is actually rising linearly, and during the off interval, of course, it is a constant value. So we are probably better off writing the current second balance as the equal areas in the positive and the negative portions. So call this area as A and this area as B, and we have to equate A equals B. Right? So writing the area A, which will be area of a triangle, it is 1/2 times the height is this 4 amperes times 4 times the base, which is D times TS. That should be equal to the area under the area B for the negative portion, and that area is just 2 here, 2 amperes times the length here is 1 minus D times TS. Okay. So the TS appearing on both sides can be cancelled, and what we have here is so this is what 2D equals 2 minus 2D, okay, or 4D equals 2, or D equals 1/2. Okay. So that is the final answer.